Okay. This session we are going to talk about constellation, the modulation. I mean, but the most important type of the most important part of the modulation is the constellation. And what is a constellation? I told you that when we have a series of bits like this, the modulation takes a k bit and turns each k bit into a symbol. For example, if I take each 3 bits, my k would be, for example, 3, and each one of these would be a symbol. For example, symbol 1, symbol 2, symbol 3, symbol 4. Okay? And we will have so many types of symbols. So with k equal to 3, we have m equal to 2 to the power of 3, which is 8. So our order of modulation would be 8, for example. Just let's make it a little bit smaller so that we can show it with 8. It's a little bit high. Let's make it 2. Let's make k 2. If k is equal to 2, each 2 bits would be one symbol, so it would be like this. Each 2 symbol is like this, and m would be 2 to the power of 2, and exactly 4. Okay? But how I can send, now I have symbols, okay? I have different symbols. My symbols would be like this. S1 would be 0, 0, S2 would be 0, 1, S3 would be 1, 0, and S4 would be 1, 1. This is how I can map bits to symbol. Okay. For example, this one, when I see this one, I know that this is 0, 1. 0, 1 is S2, so this one is S2. Okay, I'm doing some kind of mapping between bits and to mapping the bits to the symbols. So this one is also S2, this one is S3, next one is also S3, again S3. For example, if it's 1, 1, it would be S4. Okay? This is how I mapped it. And after the mapping, so I told you that we will have now the symbol rate instead of the bit rate. Now we have Rs, which is equal to log2 of Rb over log2 of n, that is, so it should be lower than the bit rate. So, but how can I mapped these bits to these symbols. I mapped them and I know that, okay, perfect, I know which bit is which symbol. So how can I physically send them to the receiver? Now the question is that how should I send these symbols? I cannot just say symbol 1. I should make it into some kind of physical form that I can send it to the receiver. So this is when the waveforms come in. Okay, so in modulation, then we map each of these symbols into one specific waveform. For example, I will tell that if I want to transmit symbol 1, I will transmit a waveform like this. For symbol 2, I will transmit a thing, this is T. For symbol 2, I will transmit this waveform, and for symbol 2, I will transmit this waveform. You see it is shifted, for example. Or I can just change the shape, and let's say that if I have symbol 1, I will send this form. If I have symbol 2, I will send this waveform. This is how remote controls work. When you want to turn on your computer or your TV, this is how it works. Your controller maps each button into some kind of waveform. So you press that button, that waveform reaches the TV, and TV knows that it has to do some specific thing. This is exactly, but if I want to transmit S0, S1 or S2, if I want to transmit S1, I transmit this one, the receiver receives this one, knows that this kind of waveform is related to S1, and it also has this mapping, so it relates to S1, so the bits that are coming to me are 0, 0. And then for S2 here, I send this waveform, the receiver sees this waveform, it knows that this waveform corresponds to S2, and then what does it mean S2? It means 0, 1. So then this way I am transmitting my bits to my receiver, and my receiver is getting my bits, and if I can transmit bits to the receiver, I can transmit everything, because everything is 0 or 1. If it's 0 and 1, I can. Computer is based on 0 and 1. If I can transmit 0 and 1, I can literally send videos, send messages, and everything. Okay, is that okay? So, how this mapping works? This mapping between symbols and waveforms is so important. In the past, I mean the older devices, in the past, this assignment between symbols and waveforms were very static. I mean, it was not dynamic. It was like the controller. Each button had a specific. It was like circuits. Some circuits are in hardware. Some circuits were mapping these two things. But now in our phones we don't have this static configuration. It's dynamic. It's based on the channel condition. This assignment makes the channel condition makes these assignments different. For example, when the channel is so good, you see that when your phone is near a base station with full antenna, when you have full antenna on your phone, you can download really fast. And when you go somewhere that has lower antenna, you download with a lower speed. That's the reason, because when you don't have enough signal power, your antenna will be lower. So your phone decides to make this k equal to 2, so it sends each 2 bit at a time. But when you go near to a base station with a higher power, it makes this k into, for example, I don't know, like 10, and it would be 124. So you will, with one symbol, you send 10 bits at one time. You send one symbol, you receive 10 bits. The other symbol, you receive 10 bits. So this way you are increasing your speed of downloading. So, but how it is managed, how I will say that it is. So now let's change to 2, and then 1 second later let's go for 5. Let's go for 10. Okay, it should be managed somehow. It is managed by the signal spaces and the basic functions. So the thing is that we are just considering the energy of the waveform. It doesn't matter, my waveform is like rectangular or sinusoidal. When I receive the waveform, I receive some kind of energy. Some kind of energy hits my device. If I can measure that energy, so and see which energy is equal to which symbol, I can understand the symbol. So it doesn't matter the shape of our waveforms for now. In this course, we will just consider the rectangular waveforms like this. Consider this is S1. For example, this is T over 2. This is T, this is our sampling time interval, and this would be T over 2, that is the time duration of this pulse. This is a pulse. And this would be the amplitude of the pulse. Okay. So if I want to send S1, I will just send this one, this waveform that has some energy, and for S2 I will send another pulse that has another energy. For example, this one. Do you agree that the energy of these two are different? This one has a higher energy. It has more energy than this because it has more time interval. So I'm sending an energy in a duration longer than this one, so I will have more energy in the receiver when I receive this. So, but by having different energies, we can receive to something that we call a constellation. Constellation determines these energies. In constellations, mainly our constellations are in 2D. I mean, it has two basis functions like phi1 and phi2. We call them phi1 and phi2, and phi(n), because we have n type of this. So in here, our dimension of the constellation is 2, which means we have two basis. We call them basis functions. Basis function. We call these phi1 and phi2 basis functions. These are the main functions that are creating our energy signals. In this way, each point in this constellation has a specific energy. Okay, if I have a point here, it has an energy that is equal to its distance from the origin, which is equal to the distance of this point, that is called S1, that exactly is S1, to the origin, is equal to square root of energy of this point. The distance between the origin of the constellation to that point. So I can just have different points in this constellation that have different energies. So you see that each one of these points have a phi1 value, that is S11 for this one, S11, which means that S1 on phi1, projection of S1 on phi1. So it's S11, and projection of S1 on phi2 is S12. You see that? So I can show this with S11 and S12. I can show this point with this. Okay, these values determines our points. So what I will do is that I receive these bits. This corresponds to S2, or I receive. Just imagine this is 0, 0. This is S1. I want to transmit these 2 bits. It's S1, so I want to transmit S1. I need the S1 energy. Where do I get the S1 energy? From my constellation. I go to my constellation, I see that I have S11, I have S11, for example, equal to something, for example, 3. I'm just giving some random numbers, it's not 3, it's there or something. And so I put 3 here, and then this one is also, for example, 3. I put 3, 3, and I just take this point and transmit the energy of this point to my receiver, and the receiver has this constellation. My receiver gets an energy, and it maps this energy to this constellation. For example, it gets an energy somewhere here. Never you get the energy exactly on the same point that you transmit. Do you know why? Because we always have noise in our channel. The channel is always noisy. So when I transmit one symbol, its energy gets a little bit different because of the noise. If noise is so high, for example, right now the noise was not so high, the point will drop here in the constellation at the receiver. It will show it up here, and right now I can say that this is most likely to be S1, not S4 or S3 if I receive this point. It's more near to S1. Do you agree? But if the noise is so high, this point might drop here. I transmitted that one, but the noise made it go here. Noise changed its energy to be more near here, and so my receiver doesn't know that. So it gets a score. It just compares the difference. It sees that the point that I'm getting is more likely to be a score, so it thinks that it's getting a score, and that's where the error comes in. In this way, we have an error. So the probability that we transmit S1 and get S4, probability of getting S4 in terms of S1 when having S1 is the probability of error. Probability of having S4 in terms of S1. Or if I call this point Y, the better way to show that is like the probability of error is equal to probability of Y equal to S4 when I'm transmitting S1, having S1. So that's the big picture idea when we say the modulation does that. Modulation takes beats, puts it into symbol, and then maps symbol into some kind of waveform that has a specific energy. Where do we get the energy from? The constellation. From this constellation, when I want to transmit S1, I get these 2 points. I get the energy of S1, and I transmit the energy of S1 into some kind of waveform. And the receiver will get that waveform, looks on this constellation. It will the receiver will measure the energy, and after that look at this constellation again, and will tell that this point is near to which of them, and that's the symbol that I get. But so, and in this way, I can just tell right now I am telling my receiver that I am using order of modulation that is equal to 4, so that it has 4 points on the constellation. If I have a better signal, I can transmit with a better quality. I have better signal quality, I can transmit with a higher bit rate. So what can I do? The only thing that I have to do is that telling my receiver that I'm transmitting not n equal 4, n equal to, I don't know, 16, or n equal to 8, for example. Because I have better condition, I have better quality. So that what happens in that condition? I will have another 4 points in this constellation. It would be S5, S6, S7, and S8. But now what is the problem? The problem comes in. Now the problem would be the noise, because right now the energy of my symbols are really near to each other. If I want to transmit S1 and the noise makes it a little bit further and it drops here, my receiver thinks that I'm transmitting S6, for example. You see that the points are getting closer to each other, so the probability of error will go higher. Probability that I get S4 in case of S1, it would be higher, because now my points are near to each other. The energies are similar. So did you get that?
No, I didn't.
Okay.
That's
Good. If you are following me, that's enough. If you are following me, then so you will go and see the video and we will get better. But okay, this way we can say that we have we made ourselves a constellation. So But the main problem is to derive this phi1 and this phi2. How do we get them? What is the formula for, what is the shape of phi1 and phi2? What is the mathematical formula of them? That's the question. Okay. So let's go to see how we get that. In most of the cases in this course, for these questions, fortunately, we are only using n equal to 2,
Okay.
which means that we have two symbols. And k is equal to 1.
Mm-hmm.
And we have two symbols, 0 and 1. That is called binary. It's a binary system. Because we have only 2 points in the constellation. We have only 2 symbols.
Okay.
So, and one of the basic ones is called binary. One of the most basic ones is called binary antipodal. What does that mean? It means that S1 and S2 have exactly equal intervals in terms of their waveform, but they have different amplitudes. So it would be something like this. S1 is that one, and S2, for example, S2 will have a different amplitude. So it would be like this is S1 and this is S2. You see that they are the same, but they have different amplitude.
Mm.
This is called antipodal.
Okay.
They can have any different number of amplitude. For example, S2 could be like this. S2 could be like, for example, A/2.
Mm-hmm.
Just have different. If we have 2 bits, if we have 2 symbols and they only differ in the amplitude and not in the time, it will call binary antipodal. That's it. So, in the most basic case, we have 2 symbols that have the same interval. Both of them are from 0 to t/2. This one is from 0 to t/2, but they have different amplitudes. This one has amplitude A, this one has amplitude minus A. So, I will clear.
Yes.
We'll cancel this. So, to derive the constellation, first I told you that we have to derive our basis functions. Basis functions are okay, these are my waveforms, and that's my antipodal waveform. So, the first thing that I should do is to derive my basis function. And before that, I have to decide how many basis functions should I need. Did you see that on the previous point? I had 2 basis functions, phi1 and phi2, that I called basis function, and from that I would take sketch the constellation. So first I have to decide how many basis functions do I need to sketch these 2. What are the basis functions? Basis functions are some kind of waveforms that from which I can generate any kind of waveform I have. Okay. So for example, for these 2, imagine if I just multiply this waveform by -1, I will get this one. So if I have this, only this waveform, I can write this one, and vice versa. Vice versa. If I have this one, I can write this one. Do you agree?
Mm-hmm.
Just by multiplying by the -1, these two shapes will be equal to each other.
Mm-hmm.
So, from this, I can understand that with one waveform, I can create both of them. Okay? And what is that waveform? That waveform is called phi1, that is my basis function, and if I want to sketch it, it would be this one. And it has some amplitude that I will just call A. But what is that amplitude? This amplitude is important.
Mm-hmm.
We have to determine. So with this one, I can also create this, just multiplying this by some number that makes it to A, and I just call it X. Okay, so we don't get confused. Multiplying X by some number will get me to A. To A degree, I can find some number that if I multiply X, it will be equal to A. Just mathematical stuff I could write. And multiply X to something, I can write minus A. And the interval is the same. So if we get I will derive the same, I will derive these energies from this.
Mm-hmm.
So now I can admit that my n is equal to 1, because with only this one, the dimension of my signal space, the dimension of my constellation would be 1, n equal to 1, because with only one waveform I can create both of them.
Mm-hmm.
It's kind of mathematical games. You see that you just want should see these waveforms and decide how many waveforms do you need to create both of them.
Mm-hmm.
And I will show you the other examples that you need more than
Okay.
one. Okay. I'm going to So, but first I have to decide what is this X.
Mm-hmm.
Okay. Before that, I need to tell you two main rules about basis functions. First rule is that they have to be orthogonal to each other. What does orthogonality mean? It means that if I have two basis functions like this, is it too small? Can you see it?
Yes, I can see.
Yeah. If I have two basis functions like this, this is for example t over 2. This is for example so you see that these two basis functions are not orthogonal. Why? Because they have some common parts in the time interval. You see, they have this. This would be t over 2. Okay,
Mm-hmm.
this part is common in both of them. So these are not orthogonal. They should not have any intersection in the time domain.
Mm-hmm.
Okay, you get that? But these two are not orthogonal. These are not orthogonal. But for example,
If you domain connect with the window.
sorry.
If you domain connect with the window.
Yeah. but these two I can call orthogonal because they don't have any common parts in the time domain. You see that it's from 0 to t over 2, it's from t over 2 to t. So they don't have any intersection in time domain. Okay? So these two are orthogonal, these two are not orthogonal. But in this case, we have only one basis function, so we don't care about orthogonality. So because we don't have any two of them, so these two should be orthogonal to each other. So if we had n equal to 2 or higher, we have to care about this orthogonality. We shouldn't have two basis functions that have same intervals. The second thing is being orthonormal. It's orthonormality. What does that mean? It means that if I have a basis function like this, for example, a is here, it's t over 2, and this is t, and this is my phi1 of t. Okay? If I have this basis function, the energy of this basis function, energy of phi, must be equal to 1. How do I measure the energy? It's so simple. I mean, in general, it's not simple because you have to derive it from some kind of integral. But I will tell you how we can get the answer of that integral much faster. It's just having the amplitude squared times the interval. This is energy of this is the energy of this pulse. Okay, just square of this, having this squared over times the interval of it. So this is the phi. So it should be equal to 1, so that it would be orthonormal. These are two rules, two important rules for basis function. So based on this, so should I
Yes.
cancel that? So based on this, I will go and find how much should be this. So first of all, I have only one basis function, so I don't need to care about orthogonality because it's between two of them, so they don't have any interference with each other. So we don't have anything to do with the orthogonality, but we need it to be orthonormal. So how I should make it orthonormal? I told you the energy of V1 should be equal to 1. So the energy is what? It's x to the x squared. I told you that the amplitude is squared times the interval must be equal to 1. Do you agree with me? This is the energy, it must be equal to 1. So how much should be that x? I can derive that x. X should be equal to, if I get that over there, it would be 2 over t. And it should be squared, so square root of that. So this would be the amplitude of x. X should be equal to the square root of 2 over t. So now I also found out how much, so now I basically have my basis function from which I can create both of the symbols. So if I have 0, I know that it's S1, I should create this one, I should multiply something by this one to get this one and translate it, the energy. So, but what should I multiply by this one to get this one? Now that's the question. So I can just write it in forms of mathematics. So I want to transmit S1. So I want to transmit S1 of t but I should multiply something by this. So I need S1 projection on phi1 times phi1 of t. I know this one, this is this. I don't know this one. I know this one, this is this. I have these two, but I don't know this one yet. I have to draw this one. So S1 of t must be equal to A. Do you agree? It's equal to A the whole time.
Mm-hmm.
You see that? The whole S1 of t the whole time is equal to
Mm-hmm.
A. I don't have this. The whole time phi1 of t is equal to 2 over t.
Mm-hmm.
So I can drive S1 1. I just should
Yeah.
make this and this way. So it would be A times square root of t over 2. So it goes
Mhm.
that way, so
Yeah.
it would be